Okay, so I'm here, or not here, to talk to you about some rootkit work that I've done. The main purpose of this talk is to talk about Tron, the Shadow Walker implementation that basically cloaks userland memory. And then there's a couple other rootkits and an IDA plugin that will help to obfuscate and hide a debugger while you reverse engineer code. First, I think it's probably important to talk about why no one's at the podium. So this is a proof of concept talk. Basically, the idea is to prove that anonymous speech is now a technical possibility. There are some social difficulties that may or may not be a major, but we'll see after the talk is over. So to make this real, make this more realistic, we're going to try to break the DMCA live and with just an act of speech using a property of Tron. So the hope is that this sort of talk format may be useful for people who are researching DRM-related crypto or censored speech in the U.S. Whistleblowers, I believe, recently had their First Amendment rights taken away, at least at the federal level. Was the Supreme Court. It's also useful to help spread awareness of privacy-enhancing technology. So let's have a look at the DMCA, at least the relevant section. It basically says, in pertinent part, that no person shall manufacture a component of any technology that either has limited commercially significant purpose other than to copyright protection, or is marketed by that person for use in circumventing copyright. So, I don't know, it seems like C would have First Amendment issues. Maybe there's some restrictions on First Amendment speech with respect to marketing, but it's definitely a huge gray area. So let's do it. Let's first talk about point B, I guess. Do free research tools have commercially significant purposes? Maybe, maybe not. Certainly Linux has commercially significant purposes. Lots of people use it in their products. But if you have a free research tool that may or may not take off, may or may not see significant use, is that commercially significant? That's not clear. So then what counts as marketing? Well, speech. How about, what if I just tell you guys the truth? It is a property of this memory cloaker that it can be used as a component to circumvent some copy protection scheme somewhere. So basically anything that relies on verifying copy protection of its code will do. All you have to do is jump past the copy protection code and then cloak that crack and then ship it with Tron, and that should work fine for anything that's doing like MD5s of copy protection code or whatever. Of course, there's better ways to do this than shipping a kernel driver with your wares. But, it's a property of this thing. It can be done. So, gotta ship the product, right? Put it on the bullet point. Put it on the feature list. All right. So we have a fair amount to cover. We have two rootkits that are useful as reverse engineering tools. A rootkit support library that includes a couple of interesting functions. We have one IDA that uses Tron, the first rootkit, to set hidden software breakpoints in your code. And then we'll talk about how all this was done, how the talk setup went, and all of that. So I guess the goal of all this is debugger hiding and covert code userland code modification and instrumentation. So if you have something that's difficult to reverse engineer, that's trying to detect debugger, or trying to detect modifications or hooks in itself, the idea is that these tools will be useful to that end. So this has applications in malware research, working with beats like Skype, DRM research, online games, what have you. The dual debugger trick presented at Black Hat was very innovative, but also a little bit of a hassle. Hopefully the IDA plugin will enable that to be done back in a single process again. And DRM research, I as an author am not liable if someone uses Tron to make a crack, I don't think. I mean, so long as I don't encourage them to do it and have a part in that, them doing it. But the DMCA does make the component or part thing kind of sticky. So, all right. So the first rootkit, Tron. Again, as I said, basically a Shadow Walker implementation, but made to work with userland memory. So it's going to hide various pages in userland memory and allow you to set permissions on them and make them appear to be something other than what they are. So let's do a quick recap of virtual memory and how this basically works. So memory is handled by the memory management unit in your CPU. And it handles the translation from virtual addresses to physical addresses. Basically, these mappings are described in data structures called page tables, which are a three-level data structure that translates your virtual address to your ultimate physical address. And because of this three-level of it, there's an optimization that caches these translations temporarily called the translation look-aside buffers. There's actually two of these, one for instructions or code and one for data. There's also a distinction between global TLBs, the ones used by the kernel, and userland TLBs. The userland TLBs are switched every time there's a process switch, but not at thread switch. So here are the page tables. This is basically the layout of how a virtual address, referred to in the Intel literature as a linear address, is translated into a physical address. For your given process, you have a value loaded into CR3 that points to the base of your page directory. The first 10 bits of your virtual address are used to index into that page directory, and then that is used to get to the page table directory, which the middle 10 bits of your address are used to offset into that. Now, what's interesting here is in the last few bits of here, there's a bunch of status bits in this table entry. Most important to us is the valid bit right at the very end. But those bits are all ignored, and the top 20 of this, or at least for the purposes of address translation, are all ignored to obtain the base address. The top 20 are used to obtain a base physical address of a page. And the last 12 bits of your linear address are used to index into that page, and that basically gets you your ultimate physical address. Okay, so let's recap how Shadow Walker works. First off, you have, let's describe the idea of this page, the page fault handler is called. It's called if your TLB lookup fails, so if your cache basically fails, and then the page table says that it's either not present or the page table says that the page you can't write or can't execute in those last few bits of that PTE. That the NMU is what detects this and then calls your page fault handler. If all these conditions are satisfied, the page fault handler is not called at all. The TLB cache is just updated by the NMU and it traverses tables for you. So what Shadow Walker does is it marks the hidden pages as invalid and then has a custom hook on the page fault handler to basically put fake or valid data in the TLBs depending on the access type and the permissions for that data. So if basically the checks are the instruction pointer of the faulting address is equal to or the faulting instruction address is equal to the faulting address, then you know you have a code access because it was your instruction that caused the fault, and you need to service that fault by caching the ITLB. And you do that basically by issuing a call to that page, or the page that you want to prime for that address. And then you issue a move to that read from that page if it's not an instruction fault. So there are some limitations to Shadow Walker. This is not me. By no means is this meant to be like a knock of Sparks and Butler's work, but there were just some things it didn't do. It didn't handle writes. The write bit wasn't checked, and if you had copy on write memory or write protected memory, you entered a fault loop or a double fault, and you had a blue screen. There are also races in the multi-threaded environment. This was addressed in their FRAC article, and they had some scheme to get around that. In userland, it turns out it can be done a little bit cleaner. Also, there was no userland support at all. It was strictly for cloaking kernel pages. And in my opinion, they sort of looked at this the wrong way as far as this cache priming technique. I think it's better to think about this not in terms of ITLB versus DTLB, like a schism between the two caches, but instead you want to think of it as sort of a schism between your page tables and what's in the cache. So your fake data, which would be in the cache, and then the hidden data would actually be in those page tables. And then you can set up access permissions, and with this thought pattern, like an API basically just flows from this that enables code and data cloaking, and which I'll show you in a bit. Also, I didn't really find it I didn't find it that useful to hide root hits. I mean, you're still hooking something. You're still hooking that page fault handler, and that can still be checked. You can still verify the code of the page fault handler. And in fact, PatchGuard is attempting to do this, but it turns out that some subtleties of the way PatchGuard works make it so that this doesn't really, or give you an opportunity rather to subvert it. So let's have a look at what hidden memory looks like. Let's think about this. So you've got, in the basic scenario that I've described so far, you do have this view. You have basically two views of a single virtual address range in userland. Notice the 7. So you can basically have your evil code in one view and then your normal code under the fake view. You also have the option to hide your evil code or evil data or your instrumentation, whatever, with null closed memory, meaning that it appears totally unmapped. If you try and access it, you get an access fault, and you basically can't detect it's there. So code permissions basically control who can access what data. And this is based on your instruction pointer, your current instruction pointer only. And so if you want to have like API calls, make API calls from allowed code, you actually have to give them permission as well, because I don't want this back in a page fault handler. That'd be just insane. So basically here in this diagram, you can see that allowed code is allowed to access the hidden memory, and then the other code is allowed to access the normal data. And then here in this null cloak scenario, you can actually have this self-allowed code that's allowed to access its own region of memory, and then fake memory appearing totally unmapped to everybody else. So